A massive bridge, thousands of tons of steel, yet one invisible force can destroy it. That invisible force is called stress. It is the silent killer of engineering. Every day our buildings fight a war against gravity and external loads. Understanding this battle is the core of structural engineering. Mechanics of solids studies how solid materials behave when forces act on them. It explains why our world stands tall or falls apart. From the smallest bolt to the longest suspension cable, every solid element must be analyzed for its strength and stability. When an external force acts on a material, internal resistance develops inside it. That internal resistance is what we call stress. At a molecular level, the bonds between atoms are fighting to keep the material together, pushing back against the applied load. Mathematically, stress is defined as the force applied per unit area of the material. It is a measure of internal intensity. This means that even a small force can cause massive stress if the area it acts upon is sufficiently small. Area is everything. The SI unit of stress is the Pascal. 1 Pascal equals 1 Newton of force acting on 1 square meter. It is the gold standard for engineers. Because structures deal with massive forces, we often measure stress in megapascals, millions of pascals, to keep our calculations manageable. Engineers mainly deal with 3 fundamental types of stress: tensile stress, compressive stress, and the often deadly shear stress. Each of these forces acts differently on a material, and each requires a different engineering strategy to resist failure. When a material is pulled apart, tensile stress develops. This is the primary force acting on the cables of a suspension bridge. Steel cables are used precisely because of their incredible ability to withstand massive amounts of tensile stress without snapping. When a material is squeezed or compressed, compressive stress occurs. This is the force that keeps our skyscrapers reaching for the sky. Columns must be designed to withstand immense compressive loads, transferring the entire weight of the building safely to the ground. When forces act parallel to the surface, shear stress develops. It is the internal force that tries to slide one part of the material past another. In engineering, shear is often the most dangerous stress because it can cause sudden, catastrophic failure in joints and connectors. Every bridge and beam must be designed to resist these stresses safely. This calculation is the difference between a masterpiece and a disaster. Engineers always include a safety factor, ensuring the material can withstand much more stress than it will ever encounter in the real world. Loads travel through structures like a chain. The stress starts in the slabs, then travels into the beams and columns. Finally, that load is transferred into the foundation and the ground itself. Every step of this journey must be calculated perfectly. To measure how much stress a material can take, engineers perform rigorous tests using the Universal Testing Machine, or UTM. These machines can apply hundreds of tons of force with surgical precision, allowing us to map a material's behavior exactly. The process starts by placing a standard specimen into the grips. Every dimension is measured down to the millimeter. As the force is gradually applied, the machine records the deformation. We are looking for the point where the material finally yields. This data is plotted on a stress-strain curve. The first part is the elastic region, where the material returns to its original shape. But once we pass the yield point, the material enters the plastic region. It is now permanently deformed and nearing failure. Structural steel is exceptionally strong, often resisting over 250 megapascals of stress before it fails completely. Every material has its limit. Understanding the ultimate tensile strength is vital for ensuring no structure ever reaches it. If engineers ignore these limits, the results are catastrophic. Materials crack, beams bend, and entire structures can collapse. In structural engineering, failure is not just an error, it's a tragedy. That's why the science of stress is so critically important. Today, we use advanced computer simulations to predict stress before we ever break ground on a new project. These digital tools allow us to visualize exactly where the stresses will be highest, allowing us to reinforce those areas proactively. The future of engineering lies in new materials, composites and alloys that can withstand even more stress with less weight. Materials like carbon nanotubes are pushing the boundaries of what is possible, promising a future of even lighter and stronger structures. But stress isn't just about one big force. It's also about repeated cycles. This is what we call fatigue. Over time, even a small stress can cause a crack to grow until the material suddenly snaps. It is the hidden danger of aging infrastructure. Modern bridges are equipped with sensors that monitor stress in real time, warning engineers before a disaster occurs. This data-driven approach is transforming how we maintain our world, ensuring our structures stay safe for generations to come. History has taught us painful lessons about ignoring the science of stress. These disasters drive us to be more precise. Forensic engineers analyze these failures, uncovering exactly why a material gave way and how to prevent it from ever happening again. Elasticity is the material's ability to bounce back. It's a critical property that allows buildings to sway in the wind without breaking. Every tall building is designed to be slightly flexible, using its elastic properties to absorb energy and keep its occupants safe. Yield strength is the point of no return. Once we pass this, the material will never be the same again. It has permanently changed. In structural members, yielding is a major warning sign. It tells us the material has been stressed beyond its design limit. Toughness is about energy absorption. A tough material can absorb a lot of energy, like an impact, before it finally fractures. We want materials to be ductile, meaning they give plenty of warning before failing, rather than brittle materials that snap instantly. Stress isn't just about weight. Environment plays a huge role. Corrosion can eat away at a material, reducing its area and increasing its stress. Engineers must account for the environment, choosing the right coatings and alloys to ensure stress levels stay safe over the building's life. Even heat causes stress. When materials expand or contract due to temperature changes, they generate massive internal forces. Expansion joints are the solution, giving the structure room to breathe and preventing thermal stress from tearing it apart. This is why we spend years studying the mechanics of solids. It is the fundamental language of the physical world we build. Every skyscraper reaching for the clouds is a balanced equation of force and area, a symphony of internal resistance that defies gravity itself. So remember, stress is always there, invisible and powerful, controlling the safety of everything we build. It is the silent partner in every engineering success, and its mastery is the mark of a true structural engineer. Behind every safe structure lies that one invisible calculation. It's the science that keeps our world standing. Thank you for joining us on this journey through the science of stress. Stay curious, stay precise, and keep building.